So taking a second look at Green's theorem for a simple closed smooth curve C that's oriented counterclockwise, we are already familiar with this relationship of a line integral around that curve C being equal to the double integral of the region R that the curve C encloses, double integral over that region of this expression, partial g with respect to x minus partial f with respect to y dA. That is Green's theorem. Now, if we're given a vector field f, big F x of y equals these component functions little f, little g of I and j, and a vector valued function r of t that defines that simple curve C in the xy plane, the question that we'd like to start with is how can we interpret these vector valued functions, big F and little r, in 3 space? And how can the line integral from Green's theorem be expressed as an integral of a dot product? Well, remember, any vector in 2 space can be expressed as a vector in 3 space simply by making that extra component equal to 0. So big F x y can be expressed as it was before, little f x y of I plus little g of x y j plus just add another component, 0k. Similarly, with little r of t, we have the components x and y is still, comma, we have a 0k component. And therefore, if we want to address the other question, expressing Green's theorem as an integral of a dot product, well, we look at these 2 pieces in the line integral, little f, little g, those are the components of f, and you could view that as being dotted with the components of dr. Remember, dr is simply little differentials dx, dy, so we could rewrite that line integral of little f dx and little g dy as the line integral of big F dot dr. Now just take a look at the way that we have been accustomed to evaluating the curl vector. To find the curl of f, we take big F and we put it in this pseudo-determinant structure, if you will. So we take the components of big F, which is little f next to the I, little g next to the j, and 0 next to the k. We put that in the last row of this 3 by 3 pseudo-determinant. And of course, we put I, j, and k in the top row to make sure that out pops another vector. And we put what's called a del operator in the middle row, which would then operate on all the component functions we put in the last row. So when we go through the motions like that, we're left with just this expression k. And why is that? Why is it that the partial derivative with respect to z, right, partial derivative g with respect to z, which should have been the I part, and the partial derivative f with respect to z, which should have been in front of the j part, how come those things have disappeared and we're just left with the k component? Well, it doesn't take much to realize that the functions little f and little g, they're only in terms of x and y, and so the partials of those with respect to z turn out to be 0. Now, we want to note that the dot product of the curl of f with k yields this expression. Once again, here's our curl. Here's our curl vector, right? Has 0 components for I and j, just a k component. So we can write it as 0, 0, this piece, which we recognize from Green's theorem, dotted with k, which just leaves us with that integrand that we are accustomed to seeing in Green's theorem. So this integrand being the right side of Green's theorem leads us to an interesting conclusion. We can conclude that we can express Green's theorem in terms of curl. So look again. Green's theorem we realized was f dot dr, and now we realize, well, that's the double integral over the region R enclosed by the curve C of curl dot k, because curl f dot k is the expression we're accustomed to seeing in Green's theorem. So you could look at it as that component of the curl vector of f in the direction of k being integrated over the region R. And another way to write that, of course, curl can be captured by the symbol del cross f, which is essentially what we did right here, evaluating this pseudo-determinant to get the curl expression. Well, the reason why we're going back to Green's theorem is because this notion of taking the double integral of the curl, or the component of curl in the normal vector direction, can be generalized. So this technique of integrating over the area of a region to evaluate a line integral can be generalized to surfaces that aren't actually in the xy plane. And this generalization is called Stokes theorem. And we recall that when the position vector r is parametrized by arc length, we have little r of s, that the unit tangent vector can be expressed as big T of s equals dr ds, which is logically equivalent to saying little dr is equal to that unit tangent vector in terms of s times the differential ds. So you could rewrite that line integral of f dot dr as f dot t ds, substituting dr with t ds. So again, this will all come together in the last theorem of our curriculum, Stokes Theorem. And Stokes Theorem goes a little bit like this. Let's see. Let little sigma be a piecewise smooth oriented surface that is bounded by a simple closed piecewise smooth curve C with positive orientation. Okay, so that is the hypothesis. Now also, if the components of the vector field big F, that is, if little f, little g, and little h, which are in front of the I, j, and k, if they are continuous and have continuous first partial derivatives on some open set containing the surface sigma, and if t, the unit tangent vector, right, t is the unit tangent vector to C, if all those conditions are met, then what we're saying is, Stokes' theorem says that the line integral about that curve C, that piecewise smooth curve C, dotted with t ds, right, equals the double integral over the surface of curl dot n ds. That's the generalization of what we saw with the Green's theorem scenario. So basically you're saying take the double integral of the component of curl that goes in the direction of the normal vector in this surface integral. And that can at times be a lot easier than integrating this line integral. Or vice versa, sometimes the line integral is easily facilitates what we're trying to do, as we'll see in some examples that will follow. So that's the best way to learn how to use Stokes' theorem. Let's look at some examples and see some situations, some nuances regarding this theorem. First of all, you may have noted that in the line integral notation found in Stokes' theorem, usually they leave out the directional arrow. A lot of times we're used to seeing the counterclockwise arrow. And the reason is because the positive orientation of a curve C is really relative to the orientation of the surface sigma. And what does that mean when you look at a diagram in 3-space? That when a person's head is in the direction of the orientation of a two-sided surface, then the surface is always on the left-hand side. If that's the case, then we have what's called positive orientation. So here's a picture. Here we have the normal vectors pointing upward. We have z equals a function of x and y. And you'll note that as this young lady is jogging around the curve that bounds this surface S, you'll notice that her left hand is always in the direction or pointing into the region. And that's because her head is pointing in the direction of the natural positive orientation. So in this particular case, the line integral would have that counterclockwise circle because that's how the positive orientation is defined in this case. So the person is said to be walking in the positive direction of C relative to the orientation of sigma if the surface is on the person's left. If the person is said to be walking in the negative direction relative to the orientation of sigma if the surface is on the person's right. So if you flipped this young lady upside down, she had her head pointed down towards the XY plane, we would have a reverse situation, and she would have to, if we wanted to keep positive orientation in that scenario, she would have to be jogging in a clockwise direction instead of what you see here in a counterclockwise direction. So I just want to take a moment to help explain why the directional arrow is often left out in the Stokes theorem that you find in most textbooks. Okay, so now also the left side of Stokes theorem interestingly corresponds to the work done by a force field F on a particle moving around the boundary of the surface sigma. So Stokes' theorem can be interpreted as the work performed by a force field on a particle that traverses a simple, closed, piecewise smooth curve C in the positive direction and can be evaluated by integrating the normal component of the curl over the oriented surface sigma bounded by C. So what we often hear when we talk about Stokes' theorem, this right side of Stokes' theorem is also interpreted as the net flux of the curl. Remember, curl dot n represents the component of curl F in the direction of the normal vector. So we're talking about a surface integral. We're talking about flux. how much of the curl vector is going outward from that surface. So when we talk about net flux of the curl, if you were talking about fluid going through a certain surface, we're talking about how much net fluid is flowing in the direction of the normal vector flux across that surface. Net flux of the curl is a nice physical way to get your mind around what Stokes theorem is really talking about. Okay. Now when it comes to computations, the preferred expression of Stokes theorem for computational purposes involves our familiar friend f dot dr, and that's often the way to go, computations that we're used to with regard to line integrals. Sometimes though the right side is a little easier to work with. Stokes theorem is often convenient for calculating work around a piecewise smooth curve with multiple sections, right? If you have a curve that has multiple sections, piecewise smooth, you could avoid all that by just looking at the right side and evaluating one double integral surface integral over the surface that's enclosed by that curve C. So it eliminates the need for a separate integral over each piecewise smooth section of the curve C. And we're now going to see with some examples how one particular perspective might be easier than the other. Now before we do, let's just take a little refresher course here as to how to evaluate curl of F, because now we're dealing with vector fields that have potentially non-zero components, little fi, little gj, little hk, and if you want to figure out curl of F, well, you put all those functions f, g, and h in the last row, you put the del operator in the middle row, and you put your I, j, k in the top row, and you do your pseudo determinant to get this expression you see here. So we're going to actually skip those details in our examples, but just wanted to make reference to how we're getting the curl vector that you'll see in the following problems. Okay, so our first one, let's evaluate the following surface integral using Stokes theorem. So the vector field big F is, let's see, this is representing e to the z squared I, 4z minus yj plus 8x sine yk, and the surface sigma is the portion of the paraboloid z equals 4 minus x squared minus y squared above the xy plane with upward orientation. So you could imagine upward arrows coming out of this surface. And here's the double integral, the right side of Stokes theorem. But since the boundary curve C is this circle, which if you were going counterclockwise about it, we would have if we were jogging counterclockwise about this boundary circle, our head would be pointing upward in the same direction as the positive orientation or the upward orientation that we were given with regard to this surface. So since the boundary curve C is that circle lying in the xy plane, we can, by Stokes theorem, say that this double integral, or the double integral that represents the net flux of the curl, could be evaluated by this line integral. So we're going to dot big F with dr, and that's how we arrive at this line integral. And you could, since you now have a picture to go on, you could put a counterclockwise arrow on your line integral because you know that represents positive orientation in this case. So going through that, let's take a look. The question is, how can we parameterize x, y, and z for the boundary curve C, which is a circle of radius 2? Well, we've seen that before. Let's let x equal 2 cosine t, y equals 2 sine t, and since we're in the xy plane, of course, z equals 0. And to go around once, you'll have t go from 0 to 2 pi. So that gives us dx is negative 2 sine t dt, dy is 2 cosine t dt, and dz, of course, is 0 all the time. So to put that line integral together, we have the double integral, the net flux of the curl is equal to this line integral over the curve C. We're going to substitute all the expressions we have here. Now z is 0, so e to the z squared is e to the 0 squared, or e to the 0. And then we have dx equals negative 2 sine t. Right? Dx is negative 2 sine t dt. We'll take the dt on the outside for all these, so this dt applies to all the things in the brackets. Then we have 4z minus y, 4 times 0, z is 0, minus y, y is 2 sine t, and times dy, which is 2 cosine t. And there is our single variable integral that we can evaluate. And that's a welcome sight, a nice single variable integral. So we distribute, let's see, integral negative 2 sine t, that's easy, 2 cosine t. What do we got? A little u sub here. Let u equals sine t to u equals cosine t dt, and do your u sub, and we have negative 2 sine squared t. Not so bad. Plug in 2 pi, plug in 0, subtract 2 minus 2. Oh well, all that work for nothing. Literally, we have an answer of 0. But that means the net flux of the curl is equal to 0. Now, looking at this problem, it's slightly different, but some things are the same. And with Stokes' theorem, if you pay close attention and slow down just a little bit, sometimes you could exploit those observations. Let's just go through the motions with this one. Let's evaluate the following surface integral using Stokes' theorem. You'll notice that the vector field f is the same as the previous problem, but this time the surface sigma is the portion of the hemisphere. Z equals the square root of 4 minus x squared minus y squared above the xy plane with upward orientation. And we want to evaluate this double integral over that surface, the net flux of the curl. Well, again, we have positive orientation, so we have the same parameterization we had last time. And we put it all together. Wait a minute. This single variable integral that's turning out here from this line integral seems to look exactly the same as the previous one. And when you think about it, how could we have predicted that we would get the same net flux of the curl even though the surface was different? Really, why should the net flux of the curl of f be the same for these two problems even though the surfaces are different? Well, it's all because of that boundary. In Stokes' theorem, the only relationships required between the surface sigma and the boundary curve C are that C be the boundary curve of that surface sigma, and that C be positively oriented relative to the orientation of the surface sigma. So if you have two surfaces, let's call them sigma sub 1 and sigma sub 2, and they're different oriented surfaces but have the same positively oriented boundary curve, then it will always follow that the net flux of the curl for each of them will be the same. So if you were able to predict that earlier, you could have avoided some computations and realized, hey, we got the same positive orientation as we go counterclockwise around the boundary circle in the xy plane. Therefore, we have to have the same net flux of the curl. So watch out for that with Stokes' theorem. Sometimes you could save yourself a lot of work. Let's take another example. So we have the same paraboloid, but this time we have a different vector field f. 2zi plus 3xj plus 5yk. I'm going to take, again, sigma to be that portion of the paraboloid for which z is greater than or equal to 0 with upward orientation again. And c is going to be the positively oriented circle x squared plus y squared equals 4. That forms the boundary of sigma in the xy plane. So let's verify Stokes' theorem. So we have our same parameterization. We know that the line integral will give us the net flux of the curl that we're looking for. So we have, oh boy, let's see, 2z. Well, remember, z is 0. So anything with a z or dz goes to 0. And that's why the first term and the last term are 0. So really all we have to focus on is the 3x dy expression. Well, x is 2 cosine t, so 3 times that is 6 cosine t. dy is 2 cosine t dt. We'll put the 2 cosine t here and the dt out there. And we have a familiar expression, integral of 12 cosine squared t. So using a little altered double angle formula for cosine, perhaps you recall the identity that cosine squared t can be expressed as 1/2 plus 1/2 cosine 2t. And now that's very easy to integrate. And we have 1/2 t plus 1/4 sine 2t from 0 to 2 pi. And we're left with 12, which was taken out on the outside, 12 times pi minus 0, or 12 pi. So we now know that the net flux of the curl is equal to 12 pi. Now, to verify that this result agrees with the net flux of the curl double integral over this surface, we have to evaluate that double integral with a positive k component, since the given non-parametric surface was told to us to be oriented upwards, right? So here's the net flux of the curl double integral. Here is our unit normal vector with a positive k component, so the outward. All we need to get is that curl expression. Well, using that pseudo-determinant structure we talked about earlier and skipping the details on that, you'll find that curl of f is 5i plus 2j plus 3k. Partial derivative of z with respect to x, I, minus partial derivative of z with respect to y, k is 2y, and we have the partial, we have just the k here that we find, okay? So once again, if we dot those things, right, and take a moment to dot those two, we'll get this expression. And then if we switch to these coordinates, we have cylindrical coordinates, which can be looked upon as polar in 3D. We'll have, let's see, substituting 10x, well, it'll be 10r cosine theta plus 4y, 4r sine theta plus 3, and don't forget the r, dr d theta. Jacobian must be maintained. So we have r goes from 0 to 2, the radius goes from 0 all the way to 2. And to go around this circle one time, we have to have theta go from 0 to 2 pi. So again, we left off with this integral. And let's move in here. Let's see, distributing the r and then integrating with respect to r gives us this expression. And we're going to evaluate that as r goes from 0 to 2. I'm skipping a little bit of the details, but showing as much as I think is necessary. And then we would get this expression after we now we're going to integrate in terms of theta, right? Before we integrated in terms of r, theta was treated like a constant, and now we're going to integrate with respect to theta as we go from 0 to 2 pi. And, well, you know it, we also get 12 pi. So we have verified that Stokes' theorem is certainly true in this case. But could we have made this connection another way and avoid some of this work? We could have saved ourselves a lot of time if we realized that this parabolic surface has the same positively oriented boundary curve C as the disk shown in this figure. Isn't a disk in the xy plane, isn't that also a surface? So this means that the value of the surface integral would not change if sigma were replaced by this surface R that has the same positively oriented circle C as its boundary. Now in this particular case, the normal vector would simply be k, pointing upwards, right? 0, 0, 1, or k, since the surface or the disk would need to be oriented upward to maintain the positive orientation of the curve C. And again, in this case, we have x equals 2 cosine t, y equals 2 sine t. Don't forget that z equals 0. So all these I and j pieces, those go to 0, and you're just left with k to give you your unit normal vector pointing upward. So that means the net flux of the curl, we could take that curl vector we evaluated earlier and dot it with this vector 0, 0, 1. And by doing that, 0i plus 0j plus 1k would give us an opportunity to evaluate a double integral, right? Switching to cylindrical coordinates. 3, what's left? Let's see, we have 3r dr d theta. Okay, if you think about that, 5 times 0 is 0, 2 times 0 is 0, 3 times 1 is 3. R dr d theta comes from the Jacobian of cylindrical coordinates. Now, this is a lot easier than the line integral we evaluated earlier. So we have the integral of, well, the evaluation now of 3r squared over 2, as r goes from 0 to 2, and that leaves us with 6 d theta. So it's the integral from 0 to 2 pi of 6 d theta, and that gives us, oh my goodness, again, 12 pi. So again, by knowing the nuances of Stokes' theorem, sometimes you could really avoid going through a lot of work like that. They need to change this to the number 1. That shouldn't be a k, that should be 0, 0, 1, but it works out here. Okay, so moving through that, again, we can see that we could avoid a lot of extra computation if we simply remember what Stokes' theorem says. So we hope you enjoyed that video. We finished the curriculum, and that's certainly a great thing. I'm so stoked about that, if you'll excuse the pun once again. And I wish you well, and hope to see you next video.